Rational function. What is a rational function? What is a rational? What does rational mean? The first 5 letters of the word spells what? Ratio. What's a ratio? Now we're going to look at fractions. We've looked at them already. We had one of them when we dealt with the library of functions. What does this graph look like? From the library of functions. Yes, how? Because we also have another one that looks like this. But let's look at it. Since it's a fraction, what's the only rule we have about fractions? Right. The denominator cannot equal 0. So whatever x makes the denominator equal 0 is called a vertical asymptote. An asymptote is a line that cannot be crossed. So what's our asymptote there? In the top one. Yeah, so x cannot equal 0. So we cannot cross that line. In this case, it's the y-axis. Now, another thing we know, as x goes to infinity, what happens to 1 over x? What happens to this number? So think about it. When x is 1, what do we get? When x is 10, what do we get? It gets smaller. Eventually it gets to how small? A number. It gets so small, it gets very close to 0. So as x goes to infinity, this number gets very small. Conversely, as x goes to 0, remember, whenever we have, as it gets closer to 0, it becomes a fraction. So this number goes to infinity. So our graph will look like this. At 1, it equals 1. That's only the positive side. What about when x goes to negative infinity? Where does 1 over x go to? It still goes to 0. Because as these numbers get bigger and bigger and bigger, it just becomes a negative, but it still gets closer to 0. As x approaches 0 from the left side, 1 over x still goes to infinity, negative infinity. So our graph on this side looks like this. We talked about that 10 weeks ago. Library of functions. What about this one? Do we have a vertical asymptote? What is it? Right. X equals 0. Or no, X, a vertical asymptote is X, so our restriction is we cannot have X equals 0. So we know that X cannot equal 0. So we have a vertical asymptote there. On the positive side, as X goes to positive infinity, 1 over X squared goes to where? Yeah, a lot faster because it's squared. When X now is going the other direction, when it's going closer to 0, what happens to the number? It goes to infinity. Because let me do this side. So this side will look like this. At 1, it equals 1. How about on the other side? When X goes to negative infinity, 1 over X goes to where? Goes to 0 also. And then as X goes to 0 from the negative side, 1 over X goes to where? Are you sure? We squared it. If you take a negative number and square it, what do you get? A positive. That's the Atari symbol. So at -1, we get 1. So let me show you. At 1 over X, here's X, here's 1 over X. And we'll do it both ways. Here's X, here's 1 over X. This is as X approaches infinity. So at 1, it's 1 over 1 equals 1. At 10, 1 over 10. At 100, it's 1 over 100. At 10,000, it's 1 over 10,000. So it gets smaller and smaller and smaller and smaller and smaller, smaller. Eventually, this number gets pretty close to 0. It gets that small. Now, when X goes to 0 from the positive side, we're looking at the positive side only right now. So let's start at 1. We have 1 over 1 is 1. Let's look at 1/2. What is 1 over 1/2? Take the top, leave it alone, flip the bottom. So there was, how many times, if you take 1 and cut it in half, how many of those you have? You have 2 pieces. When X is 1/10, what is 1 over 1/10? 10. When X is 1 over 1,000, what is 1 over 1/1000th? So the smaller this number becomes, the bigger this one becomes. So that's this one goes to infinity. And same thing on the negative side. As X goes to infinity, a negative infinity, it just gets a number, becomes negative, but it still goes to 0. And this one here, same thing there. This one goes to, the number's all negative, but they're going to negative infinity. So that's what come in this one, it's like this. When X is positive, it's positive. When X is negative, it's negative. All right. I want to give you that heads up because we're going to talk about what are called rational functions. Rational function is a function that is a quotient of two polynomials. So f of x is equal to p of x over q of x, where p and q are polynomials, and q of x does not equal 0. Here's a flash from the past. What is the domain of f of x? And then graph it. So what's this graph going to look like? Let's do the graph first, and then we look at the domain. Remember how we graphed functions? First, what is the function? From the library of functions, what function is this defining? 1 over x. Since it's 1 over x, we know the graph looks like this. Second step, is there a horizontal shift? How many spaces where? Very good. Because we set the bottom equal to 0, we get x equals 3. So we shift it to the right 3 spaces. Remember, that's our new origin. This is our new origin. So we shift from here to there. The graph still looks the same. Is there a vertical shift? No, because there's no plus minus. There's no other things. So that's our graph. Our graph is shifted over to 3 to the right. And there's our new graph. So what's our domain? When we say domain, we're talking about the x values. Is it from negative infinity to positive infinity? Can we use every x? Which one can we not use? Yeah, we cannot, because 3 makes the bottom equal to 0. So we take the denominator, set it equal to 0. That's the only one we can't use. So our domain is from negative infinity to 3, and then union 3 to positive infinity. So far, so good. Now I'm going to give you a bunch of other functions. I want you to tell me the domain of each of these functions. F of X equals, well, forget these because we just did these. The domain of this one, and we should know the domain already for these. What are they? Right, so it's negative infinity to zero, union zero to positive infinity for both of these. How about this one? What's the first thing you do? What kind of equation is at the bottom? It's quadratic. So first thing you want to do, whenever you have a polynomial higher order degree than one, factor them. The top is already factored. What does the bottom become? So it becomes x's, right? With signs?
Both the same, but it's not the one. The opposite, so it's close.
It has to be opposite because think about it. This number times this number has to be negative. Only way it's positive is if they're opposites. So now what goes here? What? Yeah, what times what is 2? When you subtract them, you get 1. So where does 2 go? Yeah, because this is our opposite sign, the bigger number gets a minus. So what are my vertical asymptotes? And, right. Once you have the vertical asymptotes, you now have your domain. If you think about it, the only numbers you can't use are those. So we go from negative infinity to -1, from -1 to 2, and then from 2 to positive infinity. Pretty easy so far. F of X is equal to 2x plus 5, 2x minus 6. We have a fraction. Can you factor anything? Yeah, the only thing, yeah, you're right. The only, but it's not going to cancel anything, but it makes it easier for us. Since we can't cancel anything, we can't reduce anything, what's our vertical asymptote? Right. So that's the only number we can't use is 3. So we can use these numbers and these numbers. Our domain then is negative infinity to 3, 3 to positive infinity. F of X equals x squared plus 3x minus 3, x squared minus x minus 2. Next step?
Oh.
Yeah, if possible. Can we factor the top? That should be two, that's not, that should be a two, I'm sorry. So let's see, the top becomes what? The signs are gonna be, what times what is three? When you subtract them, you get two? Three and one, very good. And the three goes with the plus. And on the bottom, what signs go down there? Plus and minus. What times what is two? When you subtract them, you get one. And the two goes. Does anything cancel? Good. Now, about a fraction. The beautiful thing about this one, these numbers up here are my x-intercepts. So I set those equal to zero. I find my x-intercept where it crosses the x-axis. These tell me my vertical asymptote. So the vertical asymptotes are at so if we look at our graph, we go from negative infinity to negative one and two. So we can't use these two guys. That's our domain. So our domain is from negative infinity to negative one, union negative one to two, union two to positive infinity. It seems that we've done this before, doesn't it? Because I know we had to find the domain earlier in chapter 2 and chapter 3. So we have to factor the number out and then see what's that. So factoring shouldn't be that new to us. One more. This one is 6. F of x equals negative x squared x plus 1. What's my x-intercept and what's my vertical asymptote?
So there's another one. It's
Right. Take the bottom, set it equal to 0. So x equals negative 1. So x equals negative 1. So that's a number I cannot use. So my domain is from negative infinity to negative 1, union negative 1 to positive infinity. What's my x-intercept? So the top equals 0. Remember the top, to get the x-intercept, the top equal to 0. So it's going to be 0. There's negative x squared equals 0. Change the signs. You have x squared equals 0. Square root x equals 0. What's my y-intercept? Y equals what? How do you find the y-intercept? Set x equals 0. If you set x equals 0, what do you get? 0 over 1, which is 0. So it crosses through the x-intercept, the origin. I let the cat out of the bag. This next section deals with the vertical asymptotes. So I'm gonna give you the function. You tell me the vertical asymptotes. Actually, since we've done that, tell me the x-intercept, the y-intercept, and the vertical asymptote. And the domain. Yeah, so take the top, set it equal to 0. Move that over to it. Yep, x equals 11 over 2. That's my x-intercept. It's at the point 11 over 2, comma 0. What's the y-intercept? Well, yeah, the y-intercept is only the constants. Erase everything that was an x. What are we left with? The negatives cancel, so it's 11 over 8. So it's at 0, 11 over 8. Right. So it's x, because that's a negative, it's opposite signs. 4 and 2, so 4 minus 2 is 2. And the first sign's a plus, so the 4 goes there. So x equals -4 and +2. Those are my vertical asymptotes. -4 and 2. So my domain, since I cannot use -4 and 2, my domain is from -infinity to -4, -4 to 2, and 2 to +infinity. Since our vertical asymptotes are at -4 and 2, we know we can't cross those lines. So what our graph's going to look like, and we know the y-intercept is 11 over 8, which is 1 1/8. So our graph looks like something like this. How do I know that these are going to be down here and don't cross anywhere? Because the only x-intercept we have is at 11 over 2. Where's 11 over 2? What is 11 over 2? 5 1/2. 3, 4. So what the graph's going to look like is like this. It's going to cross at 11 over 2. And then that's that. Because there's no x-intercept other than that one, This one is either gonna be above or below the x-axis. And I could just test it. I could pick a number, let's say -6, and just look at it. Will the answer be positive or negative if I put -6 in there? Let's see. If I have f of -6, 2 times -6 minus 11, -6 squared plus 2 times -6 minus 8. So it's -12 minus 11. 36 minus 12 minus 8. So it's 36 minus 20 makes it 16. So the bottom's positive, and the top is -23. So we have -23 over 16. So the answer is going to be negative. So that means all the numbers have to be below the x-axis. All right, the next one. Any questions about these? Again, as I told you earlier, it's very important to know because everything we've done in the past is now being put together here. We found the x-intercepts. We learned how to graph the functions, the y-intercepts. All these are now becoming pieces of our graph. B, h of x is equal to x squared minus 4x and x cubed minus x. Tell me the x-intercept, the y-intercept, the vertical asymptote, and the domain. It'd be 0. What would that find for us? There's a couple, yes, for the x-intercept. Set the numerator equal to 0 and solve. So we have x squared minus 4x. Set that equal to 0. But on the top, we can factor out an x, which gives us x minus 4. But before we do anything, it's always safe just to factor everything out first. And on the bottom, we have x squared minus 1. What is x squared minus 1? Do we know, can we factor that one any further? A squared minus b squared is a plus b, a minus b. This is the same as x squared minus 1 squared. So it's going to be x plus 1, x minus 1 on the bottom. But before we go any further, this is an important factor. We have x minus 4, x plus 1, x minus 1. Can anything cancel? Because right now, we're looking at our vertical asymptotes are what? -1, +1, and 0. Anywhere there's an x, you set it equals 0. But these x's can cancel. If you have something that cancels top and bottom, the x's cancel. That creates a hole at x . Well, x equals 0, it's an intercept. What is a hole? A hole is not an asymptote. We continue the graph, but we put a hole at that value where it should be. So we have a hole at x equals 0. What is our x-intercept? Our x-intercept now is at x minus 4. So our x-intercept is at 4 comma 0. That's our x-intercept. What's our y-intercept? Yes, x equals 0. What we have is 0 over 0. There's no y-intercept. Well, why not? Because there is a hole when x equals 0. And we knew that from up here because the x is canceled. When x is 0, that's the y-intercept. So we won't have a y-intercept. We're going to have a hole wherever that graph would be. What's our vertical asymptotes? Right. X equals 1 and negative 1. So our domain is from negative infinity to negative 1, negative 1 to 1, 1 to positive infinity, because we can't use negative 1 or 1. Making sense? And we'll worry about the graph later on. But I can tell you, the graph will look similar to the one we just had. We had negative 1, we have an asymptote. Positive 1, we have an asymptote. So the graph will look something like this. And there's a hole on the y-axis. That's what that means. Because they cancel. That's why we factor out the numerator and denominator. If anything cancels, it becomes a hole at that point. G of x is equal to x minus 2, x cubed minus 5x. Remember, I want the x-intercept, I want the y-intercept, I want the vertical asymptote, and I want the domain. How's this? Right, the x-intercept is pretty straightforward. It's x minus 2 set it equal, take the top, set it equals 0, so x equals 2. So the x-intercept is at 2 comma 0. What's the y-intercept? Remember, y-intercept, you set x equal to 0. If we set x equals 0, we have 0 minus 2, 0 cubed minus 5 times 0. Undefined. And this will show you why we don't have a y-intercept. Because what's our vertical asymptote? Take the bottom, set it equal to 0. We can factor this one. We get x squared minus 5. Set them both equal to 0. Well, that's the reason. The reason there's no y-intercept because we can't set x equal to 0. There's a y-intercept or set x, we can't because x equals 0 is an asymptote. That's why it's undefined there. And then for the other one, we have x squared minus 5. So solve for x squared. So x squared equals 5. X equals plus or minus the square root of 5. So we have three asymptotes. Negative radical 5, 0, and positive radical 5. So the domain is going to be these guys. Negative infinity to negative radical 5. Union negative radical 5 to 0. Union 0 to radical 5. Union radical 5 to infinity. So we have our vertical asymptotes here. This is a vertical asymptote. That's a vertical asymptote. And that's a vertical asymptote. We have an x-intercept where? At 2, 0. Square root of 5, is that bigger or smaller than 2? It's bigger. So 2 would be over here somewhere. So we have an intercept here. And then what we do, we pick values in each one of these set domains. What happens if we pick a value here, say -3? We put that in our equation, we'll get a positive answer. If we pick a number between negative radical 5 and 0, we have all negative answers. But because I'm going to define next as a horizontal asymptote, we have a horizontal asymptote that this number can't cross. And then this one. And here's a rough sketch of it. Again, the way you could do this just by picking numbers and putting them in the equation and see if it's positive or negative. This one here at -3, if it's positive, here's a question I have for you. Why do I know the graph will look like this at the very end? Why do I know that? Because remember when we did when we did 1 over x, the graph looked like this. The vertical asymptote was this, that's the vertical asymptote, right? So when you approach the vertical asymptote, it has to go to either positive infinity or negative infinity as you get close to the infinity, the asymptote. So since these are asymptotes, this one is going to positive infinity. This one's going to negative infinity. This one's going to negative infinity. So the values coming in, how do I know it's going to positive infinity? Since this one gives me a positive answer, all of these numbers here have to be positive, since there's no x-intercept. Put your bag away. You know you're looking at something. So since these are all positive, as it gets close to the asymptote, it has to go to infinity. Likewise, if I pick -1 here, all of these are going to give me negative numbers. So as I get closer to this one, the only thing it can do is go down. It can't go up. And this one here has to go down also because there's no x-intercepts. The only x-intercept I have here. So that means this one has to go down. And this one has to go up. So without knowing anything else other than that concept about asymptotes, this has to happen. So that's what we have. That's our graph. So far, so good. But then now the question is, why is this one stopped at -1? Well, that's the root. Oops. The next thing we're going to talk about are called horizontal asymptotes. In this one, we know the vertical asymptote is x equals 0. And we know the horizontal asymptote is also going to be y equals 0. Horizontal crosses the y-axis, vertical crosses. So why is it y equals 0? Well, as x goes to infinity, where does that go? It goes to 0. As x goes to negative infinity, 1 over x goes to 0. So that's how we look at, that's basically what horizontal asymptotes mean. How do we find horizontal asymptotes? Remember, we deal with rational equations. So we have a n x to the power n. These are all polynomials. X n to the power 1 dot dot dot. A1 x1 plus a0. On the bottom, let's do b's. bm. We'll do bm's. what matters with polynomials, out of all these numbers, let's look at the top. Out of all these numbers, which one has the most power to it? The leading one. Same with the bottom. So those are the ones that are important. The rest of the numbers we can get rid of. Mathematically, let's say I had a number x to the third, or x to the fifth, let's say fifth. Okay, we have that polynomial on top. And on the bottom, we have x cubed. So out of both of these, the leading terms are the most important. To figure out what's going on here, divide each term by the x to the highest degree. So to figure out what's going on in this equation, divide each term by x to the highest. What's the highest degree? Well, the highest degree is 5. So I'm taking each of these terms and divide by x to the highest degree. I'm dividing everybody by x to the fifth. Now on the bottom, we have x cubed over the top and bottom. So I'm changing everybody by the same value. Now let's look what happens here. Let's do division on each one of those. So x to the fifth over x to the fifth becomes what? It becomes 1. The next one, we have plus 2, x to the fourth over x to the fifth. Because yeah, get rid of 4 of them, so we have only 1 x on the bottom. So we have plus 2 over x. Then we have a minus. We have 3 x's on top, 5 x's on the bottom. Subtract the exponents. So 5 minus 3 is 2. So we have 3 over x squared. X squared over x to the fifth. Subtract 2, I get 3. So 1 over x cubed. Get rid of 1x. So I'm 1 over x to the fourth. And then the last one is simply 2 over x to the fifth. That's the top. Do the same thing on the bottom. So we have x cubed over x fifth. 3 x's cancel, so we have 1 over x squared. We have minus 2. Get rid of the 2 x's, so we have 3 x's on the bottom. So minus 2 over x cubed plus x over x, uh, 5 over x to the fifth. So far, so good. So our first step was divide everybody by the highest exponent. Step 2, take x going to infinity. So what happens? 2 over x to the fifth. What happens to that number? Remember, what happens when 1 over x, as x goes to infinity? This one goes to 0. So if there's x's on the bottom, that one goes to 0, that one goes to 0, that one goes to 0. All those go to 0. This one goes to 0, this one goes to 0, this one goes to 0. So we're left with 1 over 0, which is undefined. All right, so that's what's happening. So to find the horizontal asymptote, we only look at the leading terms. Only use the leading terms. Three things can happen. Okay, one. If the exponent on top is bigger than the exponent on the bottom, the horizontal asymptote does not exist. Here's the reason why. X to the third over x to the first. 1x cancels, so we have ax squared over b. As x goes to infinity, remember, this is our horizontal asymptote. As x goes to infinity, the horizontal asymptote goes to infinity. So there's no horizontal asymptote. Does that make sense? If there's more x's on top than the bottom, then the equation goes up. It never goes anywhere. Never stops. If the top exponent is smaller than the bottom, then the horizontal asymptote equals 0. It's the line y equals 0. Ax squared over bx to the fifth. We lose 2 on the bottom, so it's down to 3. So it's a over bx cubed. As x goes to infinity, then the horizontal asymptote becomes 0. So if there's more x's on the bottom than the top, it goes to 0. If there's more on top, it goes to infinity. One more condition. If they're equal. If n equals m, then the horizontal asymptote is simply the coefficients. So if we had a x to the third over bx to the third, these cancel, we're left with a over b, and that's a horizontal asymptote. Example 4. Find the horizontal asymptote. Negative 7x to the fourth minus 10x squared plus 1, 11x to the fourth plus x minus 2. So the horizontal asymptote is equal to what? Keep on going.
I said how.
No. If you had negative 7x to the fourth over 11x to the fourth,
So it's just.
so these cancel, so it's negative 7 over 11. Right. Another one. F of x equals 2x plus 3, x cubed minus 2x squared plus 4. The horizontal asymptote equals so 2x over x cubed. Can anything cancel? X's.
Right.
There's one x. So we have 2 over x squared. As x goes to infinity, what happens to this number? As x goes to infinity, that number becomes what? Well, 0. If there's more x's on the bottom, then it goes to 0. For that reason. Let's graph one. Example 6. Graph this function. 2x squared plus 1 over x squared. Now, whenever you graph something, you need to have the x-intercept, if it exists, the y-intercept, if it exists, the vertical asymptote, if it exists, and the horizontal asymptote, if it exists. So what's the x-intercept? How do you find the x-intercept? Yeah, so for the x-intercept, I take the top, set it equal to 0. So I have 2x squared equals negative 1. No x-intercepts. How do I know I have no x-intercepts? Anything squared can never be negative. If I square rooted both sides, then I would have an imaginary number. That's the reason there's no x-intercepts. So this one does not exist. What's my y-intercept? One over zero is undefined. So this one does not exist either. Because you set x equals zero, you get one over zero, doesn't exist. What's my vertical asymptote? Yeah, set the bottom equals zero, so x equals zero. What's my horizontal asymptote? They cancel. You get two over one. So no x-intercept, no y-intercept. Vertical asymptote is the vertical line. That's the vertical asymptote. The horizontal asymptote is 2. And I know I can't cross this line. I can't cross this line. So I pick a point. It's either going to be above this line or it can't be below this line. How do I know the graph can't be below this horizontal asymptote? Because there's no x-intercepts. So the graph has to be up here. It looks like this. Because no x-intercepts. It can't be below that line. Now, if this occurs, what's my horizontal asymptote? But what if I divided these? If I divided these, what would I get? Over b. That's a linear equation. I can graph that. So we have what's called an oblique asymptote. An oblique or slant asymptote. If the top exponent is equal to the bottom exponent plus 1. If it's bigger than the bottom by 1, then we have an oblique asymptote. If the top is bigger than the bottom by 1, we do long division to find the oblique asymptote. Example 7. 2x squared minus 3x minus 1 over x minus 2. Let's find the asymptotes. So what's the vertical asymptote? X equals 2. So at the bottom equals 0. How about the vertical asymptote? Or horizontal asymptote? Since it's bigger on the top than the bottom, that doesn't exist. Remember, anytime there's more on top than the bottom, the horizontal doesn't exist. But since it's bigger than the bottom by 1, I can do long division. What times x gives me 2x squared? 2x. Because we have to have x squared. So 2x times x gives me 2x squared. 2x times negative 2 gives me negative 4x. Change the signs and add. So 4 minus 3 is 1, so it's x minus 1. What times x gives me x? A positive 1. So 1 times x is x. 1 times negative 2. Change the signs. This is all I want. That's my oblique asymptote. The answer after 2 steps. Because we know we have a vertical asymptote at 2, and we have, let's look at this. We have a vertical asymptote at 2. We have an oblique asymptote at 2x plus 1. So let's graph this one. The y-intercept is 1, and the slope is 2 up 2 over 1. So our graph. So what we have to do is pick a point that's not on there. So if we picked number 1, because the graph is either going to be in here or down here. And then once we plot that point, we'll get this value here. So we have that graph there, and it has to have a mirror image. That's why that's the tough part of oblique asymptotes. And we'll pick up from here next time. We'll do nothing but obliques. Didn't get as far as I wanted to today. We still have five more examples. But we'll pick up from here after Easter. So review your horizontal and vertical asymptotes, your x-intercepts, your y-intercepts, figure out, remember all those, review all those notes.